Hi, everyone. Welcome to our last video for summer, Stats 243. In this video, we're going to talk about linear regression and lines of best fit. All right, so let's go and grab the data with the number of pages and the cost. Recall the book length and book cost data set there. And I also had a graph of it, so I'm going to put that graph in. And I'll put the correlation coefficient as well. Which was oh, did I not calculate it? I can still do that. .963. Okay, which indicates both visually and with this summary statistic, there is a strong positive correlation between length of the book and cost of the book. So we can go a step farther and we could say, how much would a 400-page textbook cost? Now we can do this visually by saying, okay, there's our 400 pages. So I'm going to guess it's somewhere in the neighborhood of $70 based on the visual. I'd guess around $70. Let's do this using computational mathematical statistics. To answer this question mathematically, we use a regression analysis. A regression analysis is basically a line of best fit where the slope and the intercept are calculated from the data. So just as a reminder, the equation for a line is y equals mx plus b, where m is the slope of the line and b is the y-intercept. If I know a line that best matches my data, I could put an independent variable value, x, into that equation and get a prediction for y. The actual process for doing this is very straightforward in R. So using R to find out the slope and intercept of this line of best fit. Okay. So here we have our data. Let's look at it again. There's X and Y. And let me go back and copy all this down here. Okay. Comparing book length with book cost and looking for a formula that would let me predict book cost based on book length. So there's our data. It's always a good idea to start with a visual analysis, which is this one. All right, so the regression analysis is a linear model because we use a model that's a straight line to model our data. And so in R, the code is LM for linear model. So I'm going to name this model. I'm going to call this lm.books. And the formula is very simple. You put your independent variable in, hold on. You put your independent variable in, then you use the tilde, which is in the upper left, just below the escape button on most computer keyboards. So it's you put the dependent variable y, and then a tilde, and then the independent variable x. You run that, and then to look at your results, do summary of the name of your model. So here's our summary. It gives you a lot of information. Most of this information we're going to skip over, but there's a couple important things that I want to point out to you. The first is it reminds you what your formula is. These residuals, we're not going to worry about them right now. The coefficients are super important. The estimate on the intercept, 13.8, that's going to be the y-intercept of your line of best fit. The estimate on your independent variable x, 0.122, that's going to be the slope of your line of best fit. Regression analysis always includes hypothesis tests, and so it gives you a p-value, which it lists as probability parentheses greater than the absolute value of t. So our intercept has a p-value of 0.079, which is pretty small. And our slope has a p-value of 8 times 10 to the minus 6. That tells us that that slope is a really good predictor of the dependent variable. And then it gives you a little bit more information. It doesn't tell you the correlation coefficient between x and y, so you have to do that separately with core.test. But it does tell you something else, which is called the multiple r squared, which in this case is 0.9267. So I'm going to transfer all of this information into the notes and then define each of those pieces of information. Let me copy this in. First, I'll copy the code. And then I'm going to copy the output. Okay, there's our output. And let's start picking it apart. Okay. First, we are looking for a line of best fit, y equals mx plus b. The estimate on the intercept is the y-intercept. B equals 13.85. The estimate on the x is the slope, m equals 0.122. So the line of best fit is y equals 13.85. Oh, sorry, I got that wrong. Let me start over. Y equals 0.122 times x plus 13.85. We can use this line to predict a y value if we are given an x value. But first, let's look at some of the other output. So the probability that what you observe is greater than the absolute value of t for the x variable is the p-value on the slope of the line of best fit. In general, we want this p-value, remember the probability of observing such a slope, if there were no relationship between x and y. We want that p-value to be small, less than 0.05. In this case, our p-value is 8.112 times 10 to the minus 6, which is very close to 0. This means that the slope is an excellent predictor of the y value when you know the x value. And then the other piece that we're going to worry about is this multiple r squared. The multiple r squared equals 0.9267 means that about 92.7% of the variation in the cost of books can be explained by the length of the book. And r squared close to 1 means that most of the variation in the dependent variable can be explained by the independent variable. In other words, knowing the x value is a very good predictor for the y value. Okay. So those are the pieces that we really care about. I'm actually gonna bold them. So let's bold that one. Let's bold that one. Let's bold that one. We tend not to worry too much about the p-value for the intercept, but it's there, and the multiple r squared. So those are the main pieces that we take away from a linear regression analysis. Okay. So using the linear regression and line of best fit to predict a y value. Here's our example. If the book is 400 pages, what is my prediction of the cost of the book? Well, all I have to do is I say y equals mx plus b, and I know that m was 0.122 and b was 13.85. So when x equals 400, y equals 0.122 times 400 plus 13.85, which equals 62.65. $62.65. This is my best guess for the cost of a 400-page book. What if the book is 700 pages? Well, then I would do y equals 0.122 times 700 plus 13.85, which is $99.25. Compare that to the cost of this book that's 720 pages, cost of $95. That's pretty close. That's a pretty good guess. So the prediction of y is a pretty accurate prediction. All right. One more thing I want to show you in R And then we're going to go through a homework question so you can practice. You can watch me go through it for practice. So we can actually visualize line of best fit very easily just by doing, well, let's plot the X and the Y again, make sure those are there. And then we just do AB line of the model. So if you ever want to do this, you're going to be doing this in a lab. The code will be in there for you to do, but that's what it's doing. And it draws that line of best fit right on there. So now if we want, we can use the line of best fit to say a $400 book looks like it's going to be about $62, $63, just like our prediction. It helps us see that some of the data seems to be far away from that line of best fit, and some of the data seems to be very close to the line of best fit. Every data set has one single line of best fit. And I'm going to show you that in just a minute once I plop this into the code. Go. So let's look at lines of best fit for the previous data sets. I'm not going to put that in the code just because it's just kind of a bit of extra, but here's our, let's see. Whoop, sorry, I hiccuped. Okay. So there's, oops, I know what I'm doing. My apologies, pressing the wrong buttons. Okay, there's our super well aligned data, and I can look at it, look at the line of best fit. All those points are very close to the line. Here's our negative correlation data. Sorry, press the wrong button again. Here's our negative correlation data. This is slightly different, but it still has a negative correlation. And there's our line of best fit. It has one, doesn't look super good, but there is one. And here is our data where we think there will be no correlation. And it's got basically a flat line, right? Zero correlation is going to correspond to a flat line. Knowing what the X value is doesn't give you any hints about what the Y value is going to be.